It is that it's time to start, and I have this, so I'm being Zoomed, so I have to be on my best behavior, which would not come easily, but I'll force myself, okay? So it's a great pleasure to welcome Vedika. She actually visited Maryland once before. She may or may not remember. And we offered her a job, and she promptly turned it down, which turned out to be the correct decision, because she went to Harvard as a junior fellow and, of course, did extremely well. So Vedika currently is a tenured faculty member at Stanford, one of the youngest tenured persons there. And she got her PhD from Princeton. And as I said, she postdoc as a junior member of the Harvard Society of Fellows, I guess for 2 or 3 years, I'm not sure. She's a leading theorist in this new subject, which is really a very recent subject, I would say not even 15 years, last maybe 10, 12 years, where people actually work directly on entanglement, and in particular entanglement dynamics, quantum dynamics are all connected. I think she started, I did not look at her severe publications or anything, but I know some of her work. I think she started on many-body localization at Princeton with Shivaji Sondhi, David Hughes, and others, and made enormous contribution to the subject of many-body localization, which was a very important subject, asking the question, do interacting disordered quantum mechanical systems, do they thermalize on their own? Are they self-ergodic? In fact, the question is still kind of open, but Vedika's work pointed the right directions, and we have done a lot of work on it, often a little bit after her work. More recently, I noticed she's doing different things, still quantum dynamics, but more towards entanglement, quantum error correction, where math, physics, computer science, they all come together. And this is, of course, in some sense, frontier, very difficult subject, but amazingly progress is being made by Vedika and others, looking at these problems from various directions. It's too advanced for me, but I keep track of what goes on. Also, in these subjects, you have to do a lot of numerical work, because when you have entanglement, you cannot really do much analytical work beyond Bell. So this work brings in many different things, but the most important thing about her is that she was born in a very important city where I was born too, okay, long after me. And then she did her undergraduate. She just finished high school there and did her undergraduate in Harvey Mudd, right? Harvey Mudd, and she's very active. I mean, if you go to any conferences, you'll see her. She's always talking. So I'm delighted to welcome Vedika Khemani as a perennial lecturer, but today, of course, is JQI seminar. So Vedika, it's all yours.
Thank you. Thank you so much. That's a very kind introduction. Yeah, I'm really delighted to be here. And I'm excited that I get the opportunity to tell you about some recent things that I've been thinking about that I'm very excited about. And we'll get to go into a bit more technical detail here as compared to my colloquium tomorrow. So this talk will be on topological quantum spin glass order. And as Shankar remarked, there are many buzzwords in my talk. He was telling me this just in the title. There's topological, there's spin glass, there's quantum memory, and then there's this thing called qLDPC codes. Okay. Seven? Okay. Okay.
And the last one I did not know, but it has something with Gallagher code, I assume, right?
Yeah. The quantum version of it. Exactly. Yeah. Yeah, so this body of work that I'll tell you about, as the title suggests, it brings together physics of spin glasses and the physics of topological phases to furnish a new type of phase, which we call a topological quantum spin glass. This is not just a new phase, but it also gives you a new type of mechanism to achieve a quantum memory, which has found realization in certain families of error-correcting codes that have been under a lot of study recently in the computer science and quantum information communities. Okay, so to step back, I think of myself as a condensed matter physicist, and a big overarching theme of this talk will be in trying to illustrate this close connection that exists between the study of many-body physics in one hand, particularly ordered phases of matter, and the study of information and computation, and specifically how we can use different types of ordered phases of matter for the robust storage of information. Okay, so Probably the most familiar example of this parallel between ordered phases of matter and information storage is the familiar magnetic hard drive, which I guess isn't used very much anymore. But in a magnetic hard drive, the two ordered states of some symmetry broken magnet, for instance, if you have an Ising magnet, then these would be the all up and all down states of the magnet. These are used to robustly store classical bits, zeros and ones. And now, even if you have some kinds of noise or fluctuations that flip some bits, because you've stored your logical classical bit in this collective state, even if some small number of bits flip due to errors or thermal fluctuations, your actual information remains protected. Okay. In recent years, there's actually been a lot of interest in a very, very different paradigm for storing classical memories, and that is via spin glass order. Okay, so this work is actually very old. Hopfield's associative memories is kind of a paradigmatic example of this type of storage. And the picture you should have in mind is that spin glasses are spin systems which have some complex free energy landscape with many global and local minima. That's kind of the first picture that comes to your mind when you encounter the word spin glass. And now you can use the different local minima of this landscape to store different types of classical memories. Okay, so this could have been in the picture that I illustrated, which was from the Nobel write-up on John Hopfield. The letter J was being used to store, was being stored as a memory, but you can have cats and dogs and whichever other types of classical data streams you want, which can be stored in this complex landscape. Okay, most of my talk will be on quantum mechanics. So to store quantum memory, which are qubits, where both the where some encoded qubit is robust to both bit flip type errors and phase errors, we need a different paradigm. Okay, and what's been appreciated over the last several decades is that encoding information in topologically ordered states, which are locally indistinguishable, allows for robust storage of quantum memories. Okay. Now, this is kind of the landscape, and you can see that there's a very conspicuous missing box there, okay? And that's the missing box that our work is going to fill, okay? Can we have a glassy mechanism for storing quantum memories, much like we have this glassy mechanism for storing classical memories, okay? And like in the top row, trying to store classical memories via spin glass order is a fundamentally different paradigm for storing classical memories compared to spontaneous symmetry breaking. In fact, spin glasses and topological orders are the two kind of paradigmatic examples of beyond Landau phases of matter. So Landau spontaneous symmetry breaking gives you classical memory, and then spin glasses and topological order are two very distinct types of beyond Landau phases that have separately occupied a lot of work, that have separately been the subject of a lot of work in many body physics, but that each give you very different mechanisms for memory as well. And in today's work, we bring together these two different beyond Landau phases into a new kind of phase, which is the topological quantum spin glass, which is again going to have this very complex landscape. But now the different states that are being stored in these local minima of the landscape are going to be highly entangled topological states, which are capable of encoding quantum memories. Okay, so that's kind of the overall picture. Before getting into the details, I actually want to, because there's multiple different themes that are being covered, I just want to give you an overview of all the results that we derived, and then we'll get as far as we get. And please interrupt and ask lots of questions. Okay, so the first results, so the blue boxes will be many body physics, the green boxes will be information. The first result is that, as I was saying, we found this new phase of matter, which we call a topological quantum spin glass. This combines features of glasses and topological order, and it gives you robust long-range entanglement and quantum memory even at finite temperatures. Okay, so usually quantum entanglement plays a very important role in describing various ground state phases of matter, but it's much more fragile at finite temperatures. These phases have robust entanglement at finite temperature. Okay. Then on the information side, this furnishes a new mechanism for achieving a quantum memory, a passive quantum memory, which is self-correction. And this ends up being the relevant mechanism for describing the physics of certain new families of error correcting codes, which have been studied a lot in the last 2 or 3 years in the CS and information theory communities, but which have a much less developed physical understanding compared to other more well-known examples of codes.
Sense is topological, right?
Yes, yes. No, I will. I will. Yes, yes. Precisely define it. In fact, one of the things, Shankar was saying it's so hard to do kind of, it's we have to rely on numerics for a lot of the works in this general area. This is, I think, the first set of works where we actually had rigorous theorems and proofs. Okay, so everything is rigorously defined and proved. And what's kind of amazing is that we were, by thinking along these lines, we were actually able to also solve a long-standing problem in classical spin glasses, which has been open as best as we know for 30, 40 years, which is to give a rigorous derivation of spin glass order, which also requires defining it rigorously, in models with finite connectivity. Okay, so there's and I'll explain what that means. But these are just models defined on graphs which are not all-to-all graphs with finite degree, if you will. Okay, local and models that are local on those graphs. And
just in classic full alphabeticity. I mean,
it's one-step replica symmetry breaking. Yeah, and the advantage of our approach is that we use very transparent algebraic properties from coding theory, which allows us to make these different statements. Whereas usually when people study spin glasses, is this very heavy machinery of replica symmetry breaking, which is powerful, but only controllably applied in certain all-to-all geometries, and also it often makes the the physical interpretation of what these replicas are doing and the correspondence from replicas to kind of physical states is often subtle and sometimes hotly debated. But in our formalism, it's very physical. We'll be able to derive the structure of energy and free energy barriers, and using that directly be able to derive these properties of spin glass order without any of this machinery. Okay, and then en route to do this, we had to prove a key technical result, which is a bottleneck theorem for quantum channels, which we expect to be of independent interest in its own right. So in the study of classical Markov chains, there's a very well-known theorem called the classical bottleneck theorem, which has been used in the analysis of classical Monte Carlo dynamics, and has found very widespread application. What we do is we define a quantum version of this in order to prove our various results. And this both allows us to give a sharp definition of quantum phases, thermal quantum phases in open quantum systems, and should also be interesting from the point of view of bounding performance of various quantum algorithms, including quantum Gibbs samplers that have been studied quite a lot in recent years by a very different community. Okay, so that's kind of the summary of the different types of things that we'll talk about. And these have been posted in these 3 sets of papers over the last year. And I particularly want to highlight Benedict Plucker, who is a postdoc at Oxford, but we started collaborating about 2 years ago, and he's just amazing. And Tibor Rakowski, who was a postdoc at Stanford, but has now started his own group at Budapest. Okay. So outline. First, I'll just start very quickly and review memory from non-glassy order in classical and quantum systems. Then I'll describe this recent breakthrough to you, which is the one buzzword Shankar didn't know about what these quantum LDPC codes are and why the memory properties are unusual. And then I'll define spin glass order, both classical and topological quantum, and then give you the proofs if you have time. Okay. All right. So without thinking about glassiness, how do we use ordered phases of matter to encode information? The standard prescription is when we use error correcting codes, which are so-called stabilizer codes. This is a JQI seminar, so I won't define every one of these, but basically you have some kind of code, and the information is encoded in that stabilizer code also defines the zero correlation length fixed point of some ordered phase of a many-body Hamiltonian, and because it's an ordered phase, that the Hamiltonian has some degenerate ground state subspace. So for instance, if you have 2 to the k degenerate ground states, which are all macroscopically distinct, which means you have to act with some large operator to go from one ground state to another, the size of that operator is called the code distance d. Then we say that this encodes an NKD code. K is the number of logical bits or qubits, n is the number of physical bits or qubits, and d is the code distance. Okay, so this triplet NKD shows up in all sorts of descriptions of various codes everywhere. The simplest example of this is, of course, these Ising model, okay, for spontaneous symmetry breaking, that has 2 degenerate ground states, the all up and the all down states, and the all up and the all down states. The Ising model is also the simplest error correcting code, which is the classical repetition code, and this has k equals 1 because you have one logical bit. The 0 and 1 states of which are the 2 ground states, and d is n because I need to flip all spins to go from one state to another. Yeah.
The code corresponds to like a zero correlation to state point.
Yeah.
So this requires an RG to be defined.
Right. But these are very familiar phases. So this is just like an Ising model. So this is like a classical Ising model, and yeah. Yeah.
It always have an R to define.
Not always. So some of these LDPC ones that I'll talk about, it'll be much less clear how to do that. But at least for right now, I'm just going to talk about the Ising model on this slide, and then I'm going to talk about the Z2 gauge theory, which is 2D topological order. And for these 2 phases, it is well defined. Okay, so for topological phases, Z2 gauge theory, you can use those ground states to encode quantum memory. Okay, and let me just do the example of the toric code, just so we're all completely on the same page. Okay, so this is the simplest, most well-studied error-correcting code. You have a stabilizer Hamiltonian of commuting X and Z type checks. Okay, so the X checks are the star operators of XXXX, the Z checks are the plaquette operators of ZZZZ. They commute with each other. On a torus, there are 4 degenerate ground states. These ground states are locally indistinguishable. They look like a loop soup in either the X or Z basis, which is the electric or magnetic basis in the gauge theory language. But these are distinguished by some non-contractible cycles which wind around the 2 different holes of the torus. These are, of course, also the ground states of this toric code Hamiltonian, which is again one of these 6 points of a deconfined topological phase of a Z2 gauge theory. And I have 4 ground states. So K is 2 logical qubits are encoded, and those the states that I've listed there, which is up, 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 down, down, up, down, down, those are the states of the logical qubit. And D is square root of n in this case, because you need to apply these loop-like winding operators to go from one of these ground states to another, which scales with the linear dimension of the system, which is square root of n. Okay. So again, to encode these quantum bits or qubits robustly, I needed this feature of topological order. Okay. So far I have talked about encoding information, okay, in ground state subspaces. However, when I start thinking about the robustness of information to errors, I need to go from just properties of ground states to properties of dynamics, okay? Because error correction is fundamentally a dynamical process, okay? What we care about is preserving this code space, preserving the information that we encoded in the ground state subspace in the presence of errors that are trying to take me out of the subspace. Okay, so this is fundamentally a non-ergodic dynamical process, and how exactly this error correction works.
Non-ergodic is coupled to the outside.
Exactly. Like ergodic would be, yeah. there's errors that are trying to take you out, and you're like wanting to stay in this very, very tiny corner of Hilbert space.
Environment, it will be detail balance has to go with, but the environment is just too big.
Exactly.
It's not practical, right? That's what.
Yes, yes. And the way in which you can encode this memory and preserve the memory cares about the nature of excitations in your system. Okay, so for the 2D toric code example that I mentioned, there actually isn't a finite temperature, thermally protected, topologically ordered phase in that model. Okay, the excitations of that model are point-like, they're deconfined. So once a pair of excitations, like say violations of the X stabilizers or Z stabilizers are created, you can far separate them without paying any extra energy penalty. Okay, so if you just take the 2D toric code and you couple it to some kind of cold bath, you're going to lose all your memory. Okay, instead you have to do this active error correction process where you have to make repeated measurements in your system, collect all the measurement outcomes, put it through some classical computer, run some matching problem, for instance, minimum weight perfect matching or whatever your favorite decoder is. This is generally a very non-local classical decoding step, and then we use that to apply some corrective unitary and do this over and over again. Yeah. Sure.
I know you know a lot about. So at Google, they're very big on this active.
Yes.
I think it's completely absurd. I think Merona is easier, although Merona is absurd also. Do you have any comment on this? Can this be done? I mean, it's, every time I go to Google, this is all they're talking.
Well, they did a very small demonstration of it. Yeah. Well, okay. So let me actually talk about some of the other. So there's So okay. So there's this. Actually, let me just mention this right now. So it's not at all practical, but there is a very recent work on if you do local detailed balance breaking dynamics to still preserve memory. If you preserve detailed balance, then you're just making the thermal state, which is trivial. But can you do local but detailed balance breaking dynamics that nevertheless preserves this? And there's been some exciting work on that recently by Ethan Lake, Margarita Davidova, and others. Okay. So this is, you can think of this as you're protecting information by processing information. The measurements and processing that you're doing are sucking entropy out of the system. Okay. The other mechanism for memory, which is going to be the subject of my talk, is just passive memory. Okay, so here the standard paradigm is that you protect information by thermally stable order. Okay, you just couple your system to some cold bath and you forget about it, you leave it there, and as long as you have order in your system, whether thermal order, whether spontaneous symmetry breaking order or topological order that's stable, then your system can preserve this memory forever. Okay, so I'm sorry for the extended introduction, but actually I'm going to spend a little bit more time talking about some basics of passive memories, because I think that'll be instructive for us when we move on. So let's go way back to just Landau spontaneous symmetry breaking, which, as we know, describes many conventional finite temperature phases, magnets, superfluids, and so on. This is a mechanism for getting classical passive memories, as I had mentioned. And in Landau symmetry breaking phases, there's the phases, the different symmetry broken states are characterized by a local order parameter, and indeed, in the ordered phase, there are multiple symmetry broken states that are related by the action of the symmetry. Right? So for instance, again, in the 2D Ising model, there's a global spin flip symmetry, which leaves the Hamiltonian invariant. And if you look at the Gibbs state of the Hamiltonian, which also respects the symmetry, just e to the minus beta h, above Tc, you're in the paramagnetic phase. So most of the weight in the Gibbs state is centered on configurations with zero magnetization, but below Tc, you get these kind of two symmetric humps for positive and negative magnetization, and those are the types of configurations on which your Gibbs state has dominant weight. Okay. Now you can use this order to define memories, okay, which is going to be, again, as I said, a dynamical process. And the words are just spontaneous symmetry breaking gives you a type of non-ergodicity in your system. Okay, so a cartoon for Landau free energy that we draw when you have this transition at Tc looks like that picture. Okay, and you have these two minima corresponding to the mostly up and the mostly down states. And these are separated from each other by a macroscopic free energy barrier. Okay. So in the mathematical stat-mech literature, the words that people use to describe this kind of phenomena is to say that the Gibbs state ceases to be unique below TC. Okay, so what does that mean? Okay, as we said, the Gibbs state is just e to the minus beta h. Okay, but there's a formal sense in which this mostly up state and this mostly down state define Gibbs states in their own right. Formalize, for instance, these textbooks by Friedli and Velenik and this Dobruschen, Lanford, Ruel formalism, all of this is on defining what it means for a system to have multiple Gibbs states, but really, you know, it's this intuitive picture that you have in mind for the Ising model, okay? So we're going to adopt a dynamical definition of Gibbs states, okay? Which is also there in these various dynamical definition inherently relies on this classical bottleneck theorem that I was mentioning to you earlier. Okay, so what is this dynamical definition? It says that, again, let me look at my Gibbs state below TC, and let me, you know, so this is in some configuration space, and you ask, where in configuration space does my Gibbs state have large weight? Okay. And below TC, we know that it has large weight on these two sets of configurations with mostly positive and mostly negative magnetization. But then these are separated by a region in the middle, the bottleneck, of very low weight in the Gibbs state. Okay, so now if you start in the mostly up state, okay, and you start running detail balance obeying Markov chain dynamics, just Monte Carlo, classical Monte Carlo dynamics, okay, you're doing some local moves, okay, but you're going to stay stuck near this all up state for a very, very long period of time, right? Because using local moves, if you want to go from this mostly up state to the mostly down state, you actually have to make some very large domain walls in the system, and you have to go through this region, this bottleneck region in configuration space, which has a very high free energy cost, right? So you can formalize this by looking at this bottleneck ratio, okay? And this bottleneck ratio is just asking, in the global Gibbs state, which is the global stationary state, what is the ratio of weights in some, you know, I can define this hump to be magnetization density, I don't know, between 0.6 and 0.8, okay? So what is the weight of the Gibbs state in this bottle relative to the weight in some bottleneck that's surrounding it? Okay, the exact definitions of this, you have some freedom to do this, to choose, okay? But now this rho Gibbs is also e to the minus beta free energy. So this ratio is nothing more than a difference in free energies between a set of configurations that define your bottle and the configurations that define the bottleneck. Okay, so this quantifies what we mean by a free energy barrier that you have to cross to go from one of these phases to another. Okay, and then for the Ising model, it's well known that this bottleneck ratio or this free energy barrier diverges with a linear system size. Okay, because you have to make this domain wall of linear system size and take it across the system. And this sets a lower bound on the memory time of your classical memory if you started in up or down. Okay, so this kind of formalism, which is very intuitive, also gives a precise mathematical way to define these different Gibbs states. Okay, and in particular, you can say that a subset, which is this configuration space, which is what we're calling these omegas, is if a subset is surrounded by some bottleneck, such that this bottleneck ratio vanishes macroscopically as you take your system size to be to infinity, then you say that that component, then omega hosts a Gibbs state component, which has diverging lifetime. Okay, a Gibbs state is an equilibrium state of the system, and all of the Gibbs state components defined using these bottles and bottlenecks actually have macroscopic diverging lifetimes, which is what you want for both defining a stationary Gibbs state and defining a memory. Okay, so I'm going to call these Gibbs state components. In the literature, this is often just called Gibbs states. We use components to distinguish this dynamical definition from this DLR definition, which can be different. Okay, and Next, a component is called extremal if you can't further subdivide this component into other subspaces separated by bottlenecks. Okay, just a aside is that the name extremal comes from the fact that the steady states of any local detail balance obeying dynamics form some convex set, and this construction yields the extremal states of this set. Okay, and once you've done all of this, you can write any steady state in your system, any state with diverging lifetime can be written in terms of these extremal states with some coefficients, and these coefficients encode the classical memory that you care about. Okay. So, okay, so then we have our active. Okay, so to put it together, in the classical context, if you were talking about the 1D Ising model or repetition code, which has no finite temperature ordered phase, then you would need to do active error correction. On the other hand, if I'm talking about the 2D Ising model or repetition code, which does have a finite temperature ordered phase, then this forms a passive memory. Yes, Jay?
Last one, did we need the decay of the bottleneck state to be like exponential at system size?
So ideally, you'd want it to be exponential in some power of the system size, so stretched exponential, which is what it is in the Ising model. But actually, for some cases, even power law is fine. It'll just give you a power law memory time, but that's still diverging with system size. Yeah. Okay, and then in the quantum context, for active error correction, we need, that's operational in the 2D toric code. And actually, if you want thermally stable topological order or passive error correction, then as far as we know, it's not like all known models have at least 4 dimensions. Okay, the quest for a 3D quantum passive memory has been an ongoing quest for many, many years. But thermally stable topological order exists in 4 dimensions or higher, and there's actually a close relationship between these problems using what are called product constructions in the information theory literature. You can in fact take products of 1D Ising models to get the 2D toric code and products of 2D Ising models to get the 4D toric code, and various properties such as the nature of excitations and the thermal stability come from the underlying input codes that we start with. Okay, so now I'm going to switch gears and describe this recent breakthrough in error correction, which motivated our work. So this recent breakthrough was on the subject of so-called good quantum LDPC codes. LDPC means low density parity check. This is a kind of generalized locality. It tells you that there is some graph on which your model will look local. Precisely, it means that if you look at the checks or the terms in your Hamiltonian, which have to be happy, then each of those checks involves only a finite bounded number of qubits. And in addition, every bit or qubit is only participating in finitely many checks. Okay, so toric code is LDPC, but this allows for more general geometries. Okay, and a good code is now defined as K and D, the number of logical qubits and the code distance, both scaling proportionally to the system size. Okay, and this is of course the optimal scaling, the best possible scaling that you can have. And again, contrast this with the 2D toric code where K was finite and D was scaling as square root of n. Okay, and that it's known that the 2D toric code is actually the best you can do in 2D with these stabilizer codes. Okay, so these good codes, which have optimal overhead, optimal robustness, you're being able to encode as many logical qubits as possible with given a particular overhead, and they're as robust as possible in a scaling sense. These provably require what are called expander graphs in order to be defined. Okay, and expander graphs take various forms. There's huge mathematical literature on the construction and properties of different families of expander graphs, but they all share this defining property that boundaries are proportional to surface areas, are proportional to volumes. A boundary is proportional to bulk in these types of geometries. Okay, so I can cut out any ball of sites of size S, and if I ask what's the size of the neighbor set of that ball, okay, it scales proportionally to the size of the volume of the ball itself, okay, which is again very, very different from how things work in Euclidean geometry, where boundaries are parametrically smaller than bulks, okay. For codes, classical LDPC codes, which are good, have been known for several decades. They found application in telecommunications, all sorts of things. They were discovered in the PhD thesis of Robert Gallagher in the 1960s and actually forgotten about for many years. And then really came into their being from this paper with Sipser and Spielman in the 90s.
That's a turbo code, right? That's not the.
No, Sipser and Spielman. So there's also turbo codes.
Like a rediscovery. I thought that happened in 1995, but maybe I'm getting the time wrong.
Oh, maybe there's a typo there also. I don't know. Or maybe you just.
It's a very interesting history because hardware did not reach the proper level.
Right.
Everybody ignored Gallagher.
Oh, yeah, exactly.
Hardware, they could not do this.
Right. So this was Gallagher rediscovery and also a different type of code, which is a Tanner code, which I'll mention. Yeah. And then, there was this like 30, 40-year wait from the classical to the quantum, okay, where people kept believing that these quantum good LDPC codes should exist, okay, with a similar scaling. Yes, and these were found only, I guess it's not so recent anymore, but just less than 5 years ago. Okay. Yes. No, they're mathematicians and computer science. Yeah, mathematicians and computer scientists. This guy, Nico Broikman, he's one of my collaborators. So he's the most physicsy of. Well, I don't know anyone else, but I have fun talking to Nico at least. Okay. All right. So as I was saying, LDPC is a type of graph locality condition. To give you just a picture to keep in your head of what these models look like, imagine that you have some kind of expander graph. So this can look like some tree-like geometry, on trees, the boundaries and bulk scale similarly, but then I have all those wispy lines at the end, okay, and the wispy lines are just saying that the boundaries are closed. There's no actual root because this expansion property should work no matter which ball of sites that you take, okay, so that's some way to close the graph up. And then, this is like a decoration of the graph. That's this Tanner code that Sipser and Spielman and Tanner talked about. So the decoration says that you put bits on the edges of the graph. Okay, so every edge has a bit. And then on the vertex of the graph, you have some generalized set of classical interactions which only involve the bits that are coming into that vertex. Okay, so only involve the edges that are coming into that vertex. So now you can see this is manifestly local, okay, because your interactions only involve some edges which are incident on that vertex. And these models have finite degree. So this automatically tells you that as long as you put a local interaction on this type of graph, you're going to satisfy this LDPC condition. And the classical versions of these codes just have some local generalized Ising interactions, Z, 4 body, 5 body, doesn't matter. It just has to be finite, okay? I can also do this on some hyperbolic tessellation, which is another family of expander graphs, which are interesting for other physics reasons. And now, to build the quantum versions of these codes, you basically have to take a product of different classical codes, okay? So you have to build something that's morally two-dimensional, has some plaquette-like structures in a way. So just like we took a product of two circles to build a torus, to go from the Ising models to the toric code, here we take a product of two of these crazy expander graphs to build what's called a high-dimensional expander graph, which has all of those different types of product-like things. And then you basically think of some generalized toric code-like model on these other high-dimensional expanders, again with commuting checks, okay? And all of the magic comes in what type of product we take, okay? So this Tillich and Zibor, they formulated what's called a hypergraph product, and that gets you a very long way towards a good code, but the code distance scaling is only square root of n rather than n, and Nico Broikman and Jens Eberhardt, they came up with a way to define another product, what they called a balanced product. And if you take that, you can actually get all the way to n. Okay.
In what sense is it generalized Ising model? I mean, can you be very precise?
I can, but that will be another. Yeah, that's another 1 hour seminar. Okay. All right. So following these developments, the question that I got interested in and spent a few years on is, what is the physics of these LDPC codes? Okay, so as Shankar was saying, a lot of this development came from math and CS, and other models of error correction are models of ordered phases, which I know and love. So now we have these fantastic, nice error correcting codes. Do they also correspond to fantastically unusual phases of matter? Okay, so that's the question that we were setting out to study. And if I'm talking about a phase of matter, then coming back to the question that was asked a long time ago, you can't just talk about a single point and its properties, which is what the stabilizer code defines. You want to talk about some stability to perturbations in order to be able to talk about a phase. And because these models have k proportional to n, so remember the ground state degeneracy was 2 to the k, so there's an exponentially large ground state degeneracy here, okay? And generally from notions having to do with the third law of thermodynamics, if you have this gigantic ground state degeneracy, you can get those at fine-tuned points, but you expect that if you add generic perturbations, then these get destroyed, okay? But actually, we were able to prove, again, theorems in this paper on parallel work by Andy Lucas's group there,
So
that
Andy Lucas has not asked Andy.
this is me, and this is, oh,
Dragging.
which one?
Only because my real name doesn't show up. Is that Andy Lucas?
This is Andy Lucas?
Andy Lucas?
Yes,
or
yes,
is
yes.
another Lucas?
Oh, yeah, this is Andy Lucas, and this is me. Yeah. That's right.
So he's not a mathematician, Lucas. He's the
No. Yes. That's right. Yeah, exactly. So what we were able to prove is that if you start with these models, and why are they, one way in which they're topological here, right, is that their ground states have all of these X and Z type checks happy. So once again, they're locally indistinguishable, but there's again some like crazy global properties that will distinguish between these different code states. And we could actually show that even though there's this massive ground state degeneracy, this ground state degeneracy is stable to any arbitrarily weak local perturbations. Okay, so you really can start thinking of these models as phases. And then you want to ask, okay, so what's the, yeah. No.
Stability, is it protected by a cap?
Yes. So it's basically we were able to generalize Matt Hastings's work to this expander. Yeah, to this expander graph setting. Yeah, and actually we were able to even strengthen Hastings's work in Euclidean graphs.
This is in this.
That's right. Yep. Okay. And just to mention it, these types of models are not just, they're obviously things that theorists get pretty excited by, but they are also starting to be attractive because various types of quantum simulation platforms actually have the ability to try to realize these tunable geometries and different types of long-range interactions that you might get if you embed these models in finite dimensions. And actually, Alicia has done pioneering work on starting to think about non-Euclidean geometries in these types of quantum simulation platforms. Yeah.
Realize this, then why don't we just use the four-dimensional Torico? The four-dimensional Torico can also be embedded.
Indeed. No, you can. Yeah, but this one gives you much more. So four-dimensional Toric code, K is still finite as you scale up system size, and D is much. So this is the scaling of K and D with N is optimal here. 4D Toric code is much worse. K doesn't scale with N in any way. But in practice, it might still be that like these are just too nasty to engineer, and you're happier with the 4D Toric code, right? Or even the 2D Toric codes. In practice, I don't know, but yeah, okay. So all right. Okay, sorry. So let me keep going. So then the question is, okay, what is the nature of memory in these LDPC codes? And there's a little bit of a puzzle here, okay? What's the puzzle? The puzzle is that many known classical and quantum LDPC codes have robust passive memories, okay? So actually, the papers that formulated these codes also gave you the local decoders that stabilize memory in these codes. And those local decoders to a physicist basically just looks like zero temperature Monte Carlo. You measure a check. If the check is unhappy and there's a local move that you can do to make it happy, do the move. Okay. However, if you try to think of the model as a phase of matter, and you look at the partition function of the model, you have a Hamiltonian, you can look at e to the minus beta h, you can get a partition function. What you find is that the partition function looks analytic at all temperatures, okay? So there's no conventional thermodynamic phase transition to some kind of ordered phase, okay? So for the experts in the room, these codes actually have no redundancies in their checks. Every check is independent, okay? Redundancy is some small number of product of checks that gives you one. So for instance, in the 2D Ising model, if you do z, 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 z around some small plaquette, that multiplies to 1, that's a redundancy. In these models, there are no redundancies. So you can do a Cramer's one-year transformation to write your model in terms of these check degrees of freedom. And if you do that, you find that you get a model which basically looks like a completely trivial paramagnet with independent degrees of freedom, which represent your checks. And this has a perfectly analytic partition function, okay? So I've told you that this is a thermally, it's a passive memory, okay? This is known. And I said initially that passive memories generally go hand in hand with thermally stable order, but here there's no apparent thermally stable order that's visible in these models at all, okay? So what could be going on? What's the resolution? Okay, and the resolution comes now from spin glass order, which indeed is another mechanism for passive memory, which is not coming from thermally stable order, okay? So now I'm going to switch to spin glasses. So when I'm talking about spin glass order, okay, again, the picture that gets invoked is some kind of rugged free energy landscape with many local and global minima. Actually, this picture of a complex free energy landscape is best understood for these all-to-all models with random interactions, for instance, the famous Sherrington-Kirkpatrick model. And then the point is that these local minima, because there's these large free energy barriers to leave this local minima, if you start with some state in the local minima, you can get trapped there. Okay, so these local minima are associated with equilibrium states with asymptotically diverging lifetimes below some glass transition temperature, which is Tg. And the key point is that this glass transition temperature need not be accompanied by any thermodynamic transition in the partition function. So this has been well appreciated in the study of classical glasses. In fact, there's a very old paper by Egerter on the Ising model on a Cayley tree, which talks about how you get these different phase transitions there, even though the partition function looks analytic at all temperatures. Okay, and this is again qualitatively different from symmetry breaking because most of these minima that host stable states are not related by the action of symmetries, and there's many, many more local minima than global minima. Okay, the global minima are things that grow out of ground states, but there's vastly more local minima. So using this type of bottleneck prescription that I was telling you about earlier, what you should think about is having these types of states, having these minima define different bottlenecked states surrounded by these, or different bottles surrounded by these bottlenecks, okay? And now we come to our first kind of precise definition, which is about classical spin glass order, okay? And it's also useful to have this definition because usually, again, as I was saying, people think about it in terms of replica symmetry breaking, and replicas are supposed to be loosely associated with these metastable states in these minima, but that correspondence is actually very subtle and even debated in many cases, which are not in these all-to-all settings, okay? So what's the definition of spin glass order? I have a decomposition of my global Gibbs state in terms of these bottles and bottlenecks, okay? And that decomposition gives me a set of weights corresponding to, you know, each bottle there. Those are my WIs, okay? Each of those WIs is less than 1. When someone says it's a complex free energy landscape, okay, the picture in your mind is some crazy rugged landscape like I was drawing, but you can formalize that in terms of these two properties. The first is, and this is a very strong definition of spin glasses. There are actually weaker definitions that you might be able to get away with. I'm going to give you this very strong one. The first says that your Gibbs state is shattered. which means there are exponentially many of these stable Gibbs state components in your system, okay? And then the second is incongruence, which tells you that almost all these Gibbs states are supported entirely at finite energy density and are not related by any symmetries of the problem. Okay, so which is to say that there's many more local minima as compared to global minima. Okay.
But there is a global minimum.
Yeah, and there's in fact exponentially many global minima because there's 2 to the k ground states and k is proportional to n.
Local minima is actually more.
Exactly. Because otherwise it would be some kind of souped up symmetry breaking. Yeah. So again, contrast this with the Ising model, which only had 2 Gibbs states related by symmetry. Okay. So these 2 properties of shattering and incongruence can be quantified by looking at the entropies of that distribution of the Gibbs state in terms of its extremal components. So it's defined by this set of weights, and you can talk about a configurational entropy, which is just the Shannon entropy of those weights, and you can talk about a minimum entropy, which is quantifying how many non-trivial components you have, and just by looking at the properties of these entropies, you can quantify what these statements that I described in words. Okay, so that's going to be our definition of classical spin glass order. Yeah.
Just to make sure that I am understanding. So this is finite energy density relative to the global minimum, right? So,
yes.
So I guess the probability of each one of these states is exponentially smaller than the global minimum.
So no individual component carries more than an exponentially tiny fraction of the weight.
Right. But they're exponentially
more.
So then,
yes.
So I was getting to is, do they ultimately contribute to the partition function or not?
Oh, yeah.
The thermodynamic level.
Not the ground states don't, but the local minimum. It depends on which temperature you're at, right? And it also
some small finite temperature.
At small finite temperature, there will be a dominant set of Gibbs states that contribute, which will not include the ground state, the Gibbs states growing out of the ground states, right? Yeah. So you have all of these different local minima, and now they can encode your logical bits. So in fact, you can encode information not just in the ground states, but in all these different minima, which can form your different patterns. And the question that we want to ask is, can you encode quantum memory in a similar way? Okay, so until now, when people talk about quantum spin glasses, they usually start with a classical landscape like this and add some kind of transverse field to it. Okay, once you add this transverse field, you can get interesting dynamics coming from like quantum tunneling and so on, but you're not going to change the nature of memory by adding a transverse field. Okay, a 2D transverse field Ising model is not a topological memory. Okay, if you want to encode quantum memory, you need to make this kind of intrinsically topological long-range entangled in some way. And that's what I'll define next. Okay, so this is my classical memory, passive, spontaneous symmetry breaking spin glass order, quantum memory, that's topological quantum spin glass order, and this is how we define it. Okay, so we prove the existence of this topological spin glass order in these quantum error correcting codes. And the definition of this quantum spin glass order is, first, it has this classical complexity of the free energy landscape. Okay, so we have these properties of shattering and incongruence that I had mentioned to you earlier. That continues to be required. But now I want to say that these minima host states that are inherently topological. So what does that mean? First, if I look at this, the state that lives in this minimum, okay, this is some kind of Gibbs state. Okay, this is a mixed state. I want to prove that this mixed state has long-range entanglement. Okay, and this was defined in a very sharp way by Matt Hastings in 2011, and it basically means that there is no decomposition. You can, for every mixed state, you can always decompose it into sum of product states, so not products, it's sum of pure states. And the point is that in a long-range entangled Gibbs state, there is no decomposition in terms of purely short-range entangled pure states. Okay, and short-range entangled pure states, for our purposes, will mean states obtained via finite depth circuit, starting from some product state. Okay, so you can prove that and in fact, the statement we prove is even stronger, which is that every state, that it's not just that there's no decomposition purely in terms of short-range entangled states, but really that almost every state that enters the decomposition has to have long-range entanglement. Okay, and then there are these embedded quantum memories, many embedded quantum memories using finite temperature states. That is best illustrated with the picture I had up there. Okay, yeah. Yeah.
Why that we can embed quantum information in?
No, not directly, because I also need this local indistinguishability property. Long-range entangled is telling you it's long-range entangled, right? But I could have a way of having like you could have some, like the toric code states, they're long-range entangled, but they also have other structure, right? Which is this local indistinguishability property. So that's the second piece here. So what is that structure? So let's see what this landscape looks like, okay? So I have, remember k was proportional to n, so I have 2 to the k ground states, okay? These ground states are, these different sectors, okay, these different ground states, these different sectors are associated with these symmetry operators, right? Like in the toric code, to go from one ground state to another, you had to act with some winding operator on a loop, and that winding operator was the symmetry of the Hamiltonian. These are what are called higher form or deformable symmetries. Likewise, to go from one ground state to another, in this problem, you have to act with some crazy non-local symmetry operator, okay? So now, if I look at my landscape, this is going to be true on any basis, whether I'm looking at it in the x basis or the z basis, you'll see that in the first symmetry sector, you have a ground state, which is a dark blue well, but then you have lots and lots of local minima, okay? And the ground state, remember, it's this locally indistinguishable model, so it looks like this loop soup or web soup. It's not just loops, it's like crazy non-local things in the graph. But then you act with some non-local operator, those are those red lines there, to get to the next logical sector. So the dark blues, all of the dark blues are related by the action of these logical operators, and all of those are locally indistinguishable. Okay, so you can use all the dark blues, which are just the ground states, to form a quantum memory. We already knew this, okay? But now I can pick up any well in my system, which is the light blue, and it has its symmetry-related partners everywhere in the spectrum, okay? So I can embed another quantum memory using all of those. And then I can pick another well, and so on and so forth, okay? And the key point is that, unlike the classical case, I can't actually encode a quantum bit that's shared between the dark blue well and the light blue well, because those are locally distinguishable. I can just measure some energy function and decide that those are different, so that'll dephase my system, okay? But I have these many, basically there's these multiplets, okay? All of the different local minima define these multiplets, and these multiplets are giving me these different embedded quantum memories, okay? So that's the definition of topological quantum spin glass order, and we're able to actually prove all of these statements, okay, in this family of models. So in the interest of time, let me skip the proofs. I'll skip through my slides at some very fast pace just to give you a flavor of what the proofs look like, okay? But the really nice geometric feature is that we're able to use the structure of energy barriers, okay, which follows directly from geometry and graphs in order to define bottlenecks and free energy barriers. So for these classical codes, you have these very, very large linear energy barriers. This is provably known, and you can really see it very easily in thinking about these graphs and asking about how do defects proliferate in these graphs. If you start from some one ground state and try to go to another, you can't just easily recombine defects. They keep growing until they get to some size, and that's really visible from some kind of picture like this. And then if you have these large energy barriers, which are extensive, an extensive energy barrier for a classical code automatically gives you an extensive free energy barrier, because free energy is E minus Ts, and entropy can be no more than extensive. So order n energy barriers implies order n free energy barriers. So at least all my code words or ground states are stable. Then you have to work a tiny bit harder to talk about the structure of energy barriers around finite energy density states. But you can also show that any two states that are sufficiently far enough and sufficiently low energy density are also separated by extensive energy barriers. And crucially, this is only like a page of algebra using the algebraic structure of these codes, triangular inequality. It's actually very straightforward. You can do this, okay? Unlike all the crazy techniques with replica symmetry breaking. And this is enough to tell me about some transitions in the structure of Gibbs states. There's in fact two transitions in the structure of Gibbs states across my, as I change temperature in these classical LDPC codes. In the first, you only have a small number of states that become stable, which are the ground states, because those have the biggest barrier. And then at an even lower temperature, you get the full kind of glass transition. We can do very large scale numerics on these types of codes, and we actually see various different transitions having to do with heating up a system starting from a ground state, that's a red curve, versus annealing a system and seeing that it gets stuck well before getting to the ground state. We can compare these numerical calculations with analytics, and the lines are basically indistinguishable. So we can do all of this stuff. And I'll just flag this part because this is an actual result, which is the new sets of results in classical spin glasses, which is using these definitions, which are much stronger than what people have talked about in the past. We can give a rigorous proof of spin glass order in finite connectivity models. Okay, so when people talk about spin glasses, those are the types of geometries they consider: all-to-all or local Euclidean lattices. That's Edwards Anderson in B. That's much more debated. And then C is kind of intermediate between those, which is a non-Euclidean geometry, but still finite connectivity. Okay, and all the rigorous proofs of replica symmetry breaking only exist for A. We were able to extend this to C. Crucially, our models don't even need disorder. Okay, they're still glassy without disorder. That you can get, this has been appreciated in the spin glass literature, but also various tricks that people in spin glasses use, like the cavity method and so on, those completely fail when your model has short loops. Okay, they require graphs without any loops, but our methods also work on these hyperbolic tessellations, which are very loop rich. So we're able to prove this using this Gibbs state decomposition, which is an explicit measure of this complex free energy landscape. And these different minima, or these different Gibbs state components, are like the replicas in this RSB, but this is much more direct because we directly talk about energy and free energy barriers. And that's why this proof method is transparent. It implies RSB, but it's completely orthogonal.
But you don't replica anywhere in your proof, right?
No.
Just in the connection, because replicas
Exactly.
ideas exist.
Exactly. That's right. Okay, and then to get to the quantum one, we take these products of classical codes. That requires some extra step because the barriers actually become weaker when you take the products, and you have to prove this quantum bottleneck theorem, which has various subtleties, and then we need to prove that these Gibbs states are going to be long-range entangled. So that was a lot of other work. That is actually the technical meat of the work. This is this quantum bottleneck theorem, which is again non-obvious because you need to take into account things like tunneling and interference and coherences, which the classical bottleneck work didn't need to take into account. But we were able to do all of that and prove this. So let me, this is the last slide. So as I told you, we found this new route to quantum memory via this new phase, which is the topological quantum spin glass. This is the physical description or the physical picture you should have in mind in thinking about what these new families of codes mean. Okay, like if someone tells you toric code as a condensed matter physicist, I think V2 gauge theory. Now when someone tells me qLDPC code as a condensed matter physicist, I think topological quantum spin glass. Okay, so that's what we have, and the geometry of these expander graphs played a key role. And in general, in starting to think about these more, these different routes to get glass is obviously a type of non-equilibrium phase, but it's a non-equilibrium phase coming from free energy barriers. We can also get different types of non-equilibrium phases through detailed balance breaking dynamics, and this quantum bottleneck theorem can help us prove things about those. And finally, there's been this long quest to get a quantum memory in 3D, and these ideas of glassiness might prove useful there. I'll just leave up the 4 theorems that we talked about. Okay.
So this was quite a tour de force, physics, computer science, and math coming together. So a quantum computer did not make any company in profit, last 25 years. And I assure it's not going to make any company in profit next 25 years either. But it has done something amazing. It has brought quantum entanglement, computer science, and math very close together. Almost everything Vedika talked about, I don't think could have happened without quantum computing push. I mean, it started with Ives' work, but it continues. And that's an amazing intellectual frontier. So quantum computers already paid. It's paid. It's really, it's something amazing in some sense. I'm sure Vedika will take questions. I know she likes answering questions. So we'll take a few more questions. Yeah, this and then, yeah, please.
Thanks for the nice talk. Is the constant rate actually necessary for this physics?
No. So we started off by thinking about those problems, but as you saw, I guess I don't know of a problem in which this exists, which doesn't have constant rate, but the glassiness cares much more about the local minima than the global minima. So yeah.
If I want to understand I want to try to understand the robustness of, I guess, the topological quantum spin glass versus LDPC. I mean, and of course, this is partly because as a condensed matter theorist, I'm used to thinking about not these hyperbolic kind of systems where the volume and the area are the same. So, but then ultimately, you're going to realize this in some, as you like showed Misha Lukin's like Rydberg atom array or something like that. Where,
or Alicia superconducting.
Hyperbolic. So the question is, and I guess the question is then how we're thinking about that. So how does the error? So you have a distance d, right, in the qLDPC. Yes. This is in the standard graph.
Right.
If I translate it back to, let's say, one of these physical platforms that live in 2 dimensions.
Okay.
Like how, like, and then I can imagine there are error terms that show up which are vastly non-local and don't obey this.
No, good. So okay, so the error terms that we consider in the proof is they're local on the geometry defined by the code. So you have your code, the code has that graph. And if you embed it into 2D, you'll have those long-range connections, as you're saying. But the allowed set of perturbations are perturbations that are local on that graph. So if you have this 2D system, there are some set of long-range perturbations that are going to be ones that are natural to the expander graph. But then if there are other kind of generic long-range perturbations just in native 2D, there we don't know the stability to those. Okay, so that's one statement. And the second is like, we prove things about the stability of ground states, but actually to prove the stability of the glass, you want to prove stability of bottlenecks, which is saying like if you had all of these barriers, do the barriers also remain stable? And doing this for finite energy density barriers is more challenging, but again, we were also able to do that. Yeah.
But for the perturbations that are local in the expander.
Correct. Yeah.
There's a question right here. Yes, please go ahead.
Thanks for the earnest talk. Maybe a related question, it's a bit different from what you talked about. Like, suppose there is a structure that someone claims is like a topological spin glass. Like, is it obvious? Is it clear? Like, how I can verify it? Like in a realistic setting, meaning that if the operations are not perfect, like, is that?
Yes. Okay. So you're asking what are the order parameters for this phase in some sense, right? Yeah. And actually, even for classical spin glasses, there's some kind of point to set correlation functions which diagnose the phase, which were developed actually much later. So for our problem, one, that it's a glass, you would do some kind of heating and cooling numerics or experiments, like I was saying, like you try to anneal, you see, do you get stuck in the ground state or not? So your system should display glassy behavior. So that aspect is easy. To verify the long-range entanglement is harder. If you already knew the problem that you're thinking about, like you knew that, okay, these are the types of checks, then you could do a memory experiment, right? Like you can actually prepare the ground state, and if it encodes a quantum memory and that memory remains stable, then you're fine. But actually, the diagnostics of that memory in terms of some generalized Wilson loop web operators, that's actually much less understood even for finite temperature topologically ordered phases in Euclidean dimensions, because this area law versus volume law scaling of Wilson loops, all of that starts breaking down at finite temperatures. And it's even worse here when area and volume doesn't scale the same way. So there's a lot more work to be done in finding those topological diagnostics. Yeah.
I think that we the one talked already, that is Stanford again, and she's around. Can have questions.